Pre-calculus, lesson 1.8, inverse functions. So far in this unit, we've been talking about functions and defining them, including their composition and operations with functions like we did in the last unit or lesson. In this case, we want to talk about the inverse of a function if it exists. If you consider the word inverse, a lot of you will think of the word opposite. And so, to define this in terms of functions, though, what we're going to do here is that if we let f and g be two functions such that f of g is equal to x for every x in the domain of g, and g of f of x is equal to x for every x in the domain of f, then this means that the function g is the inverse of the function f. And this is denoted as f to the negative 1 power, and this is read as f inverse. Thus, f of f inverse of x will equal x, and f inverse of f of x also equals x. Which is another way of saying that these two functions will just undo each other's operations, leading us back to the original variable of just x. One thing to also note here is that the domain of f is equal to the range of f inverse, and vice versa. This just means that the domain and range of the original function is switched for the inverse of the function. So to verify that two functions are inverses, what we want to do is do the composition of both the two functions and make sure we get out just x. So for example, if we were to take f of g of x, well, this would mean that if we go ahead and substitute in the entire expression of g of x, which in this case is x plus 7 divided by 4. Notice in this function we have the operations of addition and division. To evaluate this, we're going to take the entire expression of x plus 7 over 4 and put it in for the x value in f, meaning we're going to take 4 times x plus 7 all divided by 4 minus 7. And so if we go ahead and simplify this, we'll notice that the 4's, since we're multiplying by 4 and dividing by 4, are going to cancel each other out, leaving us with just x plus 7 minus 7. And if we go ahead and simplify that, then we're just going to get out x. So f of g of x is equal to just x. If we go the other way and do g of f of x, then this means we're going to go ahead and substitute in the g of 4x minus 7 and take that 4x minus 7 and put it in for the x and g, giving us 4x minus 7 plus 7 all divided by 4. But this means here that the adding 7 and subtracting 7 are going to cancel each other out, leaving us with 4x divided by 4, which also cancel out, leaving us with x. Thus, since both compositions equal just x, that means f and g are going to be inverses of each other. Notice that f of x has the operations of multiplication and subtraction, which are the complete opposites of the operations found in g. Now, in the case that a function does have an inverse, these are our steps that we can use to find the equation of that inverse function. Step 1, we're going to replace f of x with y. This just makes it easier for us to work with y as a variable instead of f of x. From there then, what we're going to do is swap the locations of x and y in the equation. From there, then what we want to do is solve for y, meaning get y by itself on one side of the equation. If this equation does define y as a function of x, then the function f does not have an let me repeat that. If this equation does not define y as a function of x, the function f does not have an inverse function, and this procedure will end. If this equation, though, does define y as a function, then this means that f has an inverse. In that case, then, what we're going to do is replace that y with f inverse of x. We can always verify that the inverse function we found is the actual inverse of f by doing function composition. For example, let's consider the function 2x plus 7. We're going to try to find its inverse. To start with, we're going to go ahead and replace the f of x with y, so we get y equal to 2x plus 7. From there, then, we want to go ahead and swap the location of the x and y variables, giving us x equal to 2y plus 7. And then from there, then, we want to get y by itself by subtracting over the 7 and then dividing by 2. Since in this case that this equation does define defines y in terms of x, then this means that the function does have an inverse. And so our inverse function is going to be x minus 7 all divided by 2. In our next example here, let's consider the function the square root of x minus 2. Step 1, again, we're going to replace that g of x with y. And then we're going to swap the location of our variables, giving us x equal to the square root of y minus 2. From here, since the most outside thing trying to get y by itself is the square root, we're going to undo that by squaring both sides, which will give us x squared equal to y minus 2. And so finally, the last thing we need to do here is add 2 to the other side. So we can rewrite this as in this case, g inverse of x is equal to x squared plus 2. Now, we have to remember, though, that we also talked about domain and range of functions. If we consider the original function g of x equal to square root x minus 2, if we think about our knowledge of domain, the domain of a square root only goes from the restricted value off to infinity, depending on the direction that it's heading. So for the direction of g of x equal to square root of 2, the domain is, since it's shifted right to, would be bracket 2 to infinity, with a range of bracket 0 to infinity. This means then for the inverse function that the domain and range is flipped. So that means then that for our inverse function that we found, we need to go ahead and swap the domain and range. So the domain of our inverse function is going to be restricted to just 0 to infinity. In our last example here, we're going to go ahead and in this case we get the cubic x cubed plus 3, which is a function. So if we go ahead and replace the g of x with y and swap the variables, we'll note to get y by itself here, we need to subtract over the 3 first using our order of operations. But then to undo the cube, we're going to use a cube root. This right here will give us the cube root of x minus 3 equal to y. And since the domain and range of the original function is all real numbers, we do not need to do a restricted domain on this inverse. So we just get our inverse function here to be g inverse of x equal to cube root of x minus 3. Notice once again that they have the opposite operations. Now, when a function has an inverse, we also want to know if that inverse function is actually a function itself. So what we have developed is the horizontal line test. Similar to the vertical line test, which told us if an equation was a function, the horizontal line test will tell us if it has an inverse function. A function f has an inverse that is a function if there is no horizontal line that intersects the graph of the function f at more than one point. For example, if we consider the graph of A here, notice that if I draw a horizontal line, it's going to go through the graph touching at more than one location. This right here means that this function does not have an inverse. On B though, I can draw multiple horizontal lines, and each of those horizontal lines are only going through the graph once. This means here that this graph, by the horizontal line test, will have an inverse function. There's also a relationship between the graphs of the function f and the function inverse. We note that the graph of f inverse, if we graph the original and we go ahead and graph the inverse function as well, we will note that there is symmetry along the line y equal to x, which is the positive diagonal line going through the origin. And so we get that f inverse is just a reflection over this line. This helps us graph these functions. For example, if we consider this function right here, we notice that we're given it some very specific points. To graph the inverse, what we're going to want to do then is go ahead and reflect it over the line y equal to x. But this is the same thing as just swapping the coordinates. So the first point in our inverse will be -2, -4. And then we also get 0, -3, 1, -1, 3, 0, and 4, 4. And if we go ahead and plot those points and connect them, we'll see that we get the reflection over the line y equals x. This right here is a way for us to always confirm that we found the correct function found the correct inverse of the function by graphing both the original and the inverse to see if it has a symmetry. Please pause here and go back to any examples if needed.